Hello. I think everything is ready. Let's see. Do you see the desktop? Do you hear me? Does everything seem okay?
Yeah.
Okay, great.
Yeah.
Okay. All right. So, okay, as it says here, today that there's the exam. The exam, I can't show it to you because I don't have access to your version of Brightspace, but the exam will be available on Brightspace as soon as class is over with. Okay, and it'll be a PDF document. Oh, actually, I can show you. I can show it to you on my computer. Um, Here's what it looks like when you can download. See, the first page is instructions, and then the exam looks like any regular exam. It looks like this. You can download it, write your answers on the sheet, and scan your answers and upload them. Or if you want, you could write your answers in like a Word document and submit the Word document to Brightspace. So if you want, you can either write your answers in longhand on here and then scan it in, or if you prefer to do it electronically, which is actually kind of like the best thing in a way, you could just I, uh, you know, copy and paste the problems from here into a Word document and solve them in a Word document or a Google Doc or pretty much anything, or a text file even. Even a text file will work for this. Okay, so the exam will be, and here's just some instructions on submitting the exam back to Brightspace when you're done. Okay, so it just looks like a regular exam. It's got 8 problems. Okay, right? So it just looks like a regular exam, and you got till it's due at 11 o'clock this evening, and submit it on Brightspace just like you submit homework assignments. So when you're done, you download it from Brightspace, not from the website. You download it from Brightspace, but you submit it back to Brightspace just like the homework assignments. Okay. So anybody got a question? Anybody got a question about the mechanics of this exam? Oh yeah, we'll do review problems we'll look at a couple review problems in a second. But has anybody got a question about the exam itself, about just the mechanics of doing the exam? Anything about that before we go on to like look at some review problems? Anything? Okay, so let's look at a couple review problems. Okay. Okay, so let's see what 15. Okay, what's the difference between user mode and kernel mode? Well, okay, that that's directly out of the book. That's a really core thing. The answer is real simple. User mode, the CPU is restricted in what it can do. Okay. Kernel mode, the CPU is unrestricted in what it can do. Okay. So it's a bit in the CPU that determines whether the CPU can do anything or not. Okay. So when you're in kernel mode, that's the kernel mode is supposed to be for executing the operating system's kernel, which means that the CPU can do everything, like initiate I/O operations. If you look at it from the point of view of some of these pictures we drew, I'm looking for one of a picture that. Yeah, this bit, the CPU, when it's in kernel mode, can read all of memory. That's one example of an unrestricted thing. It could read and write all of memory. When the CPU is in user mode, it can only see the memory that belongs to that process. So like this memory belongs to one process. And this is part of the CPU. What we haven't learned it yet, but the memory management unit is what keeps the CPU from seeing other parts of memory when it's in user mode. Okay, same thing with the I/O devices. When it's in kernel mode, the CPU can talk to the I/O devices. When it's in user mode, the CPU cannot talk to these I/O devices. If you try to execute the CPU instruction that talks to an I/O device, the CPU will halt. and with an error. It'll crash your program. Okay, so user mode is restricted mode, kernel mode is unrestricted mode. Okay, and and why is this important for an operating system? It's what lets you write an operating system. Without that distinction, there'd be nothing to stop this process from taking over the CPU. If there was, when you were running this process, if you were in essentially kernel mode, this process could erase this process from memory. It could take over the CPU. It could take over the hard drive and read and write everything on the hard drive and erase everyone's files. If there was no restriction on what the CPU could do when you're in user mode, any process could completely take over the computer. Okay, so there would be essentially there'd be no operating system. Okay, and it says, like, give an example of something that can be done in kernel mode it cannot be done, and explain why it's important. Well, that's what I just said. In kernel mode, you can't. In kernel mode, you can read and write all memory locations. In user mode, you can't. And the reason that's important is because if this guy could read and write all memory locations, he could erase this guy from memory. In kernel mode, you can talk to the I/O devices. In user mode, you can't. And that's important because if the user mode could talk to the I/O devices, the user mode could take over everyone's files and delete important files and read important files. Okay. And on your computer, you might be wondering what's the big deal. But you have to remember these operating systems are used on the cloud systems, for example. You know, you don't want you don't want some company to be able to run programs on a cloud and read every other company's data. That's where this stuff becomes super important. Is this program might be a program that's a bank program, and this program is a program that's a hospital program, and they're running on a computer in Amazon's cloud. And this is exactly what's happening right now. Literally, this would be a CPU on Amazon's cloud. This program is a bank doing some of its I processing. Maybe it's running its internet banking operation, and this would be some hospital running its patient record system, and they're literally running on the same computer. And it's up to the computer to make sure that the bank data can't be read by the hospital program. Okay, so it's very important that one process can't see or do anything that affects another process. It's not so important on your home computer. Microsoft became a billion-dollar company selling an operating system that didn't do this. The early versions of Windows and DOS were not true operating systems. They didn't have user mode, kernel mode. So any process could do anything it wanted to any other process. And that actually didn't matter on a personal computer sitting at home. It only mattered in the sense that if your Word program blew up and crashed, it would crash everything on the computer. If one computer program crashed, everything crashed along with it. And there actually was a small danger, and this happens sometimes. If a program went buggy, it could delete files from the hard drive that were protected files. There were cases where people would lose all the data on their hard drive because some program was buggy. And there literally were cases where a program would delete everything from the hard drive accidentally because of a bug. So it did matter a little bit back then but it didn't matter a huge amount. But it matters a huge amount when you run uh, multiple companies' programs on a single computer, like in a cloud system. Okay, so that's what 15 is about. What about 30? Okay, um, this problem requires that you read up on the definition of these words here. Okay, okay. So, oops, there's a good explanation of what they mean. Okay, that's a pretty good. If you just Google those words, this is actually a nicely written explanation of what are the stack, heap, uninitialized data, initialized data, text in a program. Okay, all right. So, and we've mentioned this stuff in class kind of off and on, and it's actually kind of it's really kind of like a basic thing about C, that this is how C programs are laid out. Okay, this here real quick. Text is your program. When your program is compiled, it's compiled into machine code. The machine code sits in memory somewhere. The memory area where the code is called the text area. So all the code is in one place in memory. That's the text area. In this picture, he shows that is here. That's where all the code is. All the code is down there. Okay. Then the data is, well, data means variables, but what it really means is the global variables. So that's these guys here, global variables, variables that are not part of a function. Okay, so data is the global variables. Okay, and that's explained in here too. Now, there's actually a difference between uninitialized and initialized global variables. So, for example, this global variable has got an initial value. Now, remember in C, if you don't give a variable a value, it's got garbage in it. Okay, so this is an uninitialized global variable. This is initialized global variable. The difference is that this data is stored in the EXE file. So when the EXE file is read into memory, this variable gets initialized when the program loads. So that's its own area. See, in this thing here called the initialized data, which is usually just referred to as the data, that gets filled in when the program started up. Whereas this doesn't get filled in, it just gets left empty, which means it's just full of garbage. So the uninitialized variables are in their own memory locations so that they don't, so all the things that don't get filled in are in one place, and all the things that do get filled in when the program launches are in a different place. So there's a section of memory for the filled in global variables, the section of memory for these, well, he says that they are initialized to 0. And most modern compilers do that. In the original version of C, this thing would be holding garbage. But there are some versions of C that will now initialize the uninitialized stuff to 0 for you. And so in his picture, he does say that the uninitialized stuff is initialized to 0, which some compilers will do that now. And the initialized stuff is initialized with whatever your program said it should be initialized to. But that has to be stored in the EXE file. So that information that the variable B is 25 is in the EXE file and gets copied into memory. Okay. So this is the initialized data, and this is the uninitialized data, global variables. Initialized global variables, uninitialized global variables. Stack is where your local variables are. As the program runs, it creates variables on the stack. That's what the visualizers shows us. When we watch these programs in the visualizers, we see the variables being created in the stack. And the heap is where your variables are created when you do malloc. Okay, so over here, the stack grows as programs allocate and deallocate variables. So this stack grows and shrinks as you call functions, this grows. As the functions return, it shrinks. And the heap is where you malloc things from. And it grows if you malloc something really huge, it'll grow to make room for the really huge thing. Okay, if it doesn't need to grow, it doesn't grow. If you malloc a bunch of small things, it won't necessarily grow. But if you all of a sudden malloc either a huge number of small things or you malloc some really big thing, this could grow. And if these guys meet, your program crashes. Yeah, if the stack is growing this way and the heap is growing this way, and that's why there's put this empty space here. That way, if you don't use much stack space, you could use the heap space all the way up to here. On the other hand, if you don't use much heap space, you can use the stack space all the way down to here. On your hand, if you try to use a lot of stack and a lot of heap, they might meet in the middle, and then your program crashes. Okay. All right. So then down here, here's a little bit of code, and you have to figure out from looking at the code where every one of these variables go. And essentially, you just use the definition of these things. Okay. So A is a global variable. See, now this means the address of A, which is its memory address. See, these are, now I didn't put A here, I put the address of A to say, well, I want where is it in memory? Where is it in memory? So the address of A is a memory address. But by definition, that's an uninitialized global variable, so it's in the BSS. Okay. Now what's B? B is a global variable that's initialized, so it's in the initialized global variables. What's C? Notice I didn't put address. I didn't write address of in front of C because C is the name of a function, and in the C language, functions are addresses. Okay, you don't have to write. You can put an ampersand in front of the C, but it doesn't change the meaning. But by definition, C is the address of the code. So that's code. So that's in the text segment. Okay, it's a funny word. I mean, why did they call it text? But this all these names were picked back in the 60s. Okay, so these names have been like the word heap. Like, why in the world is it called a heap? I mean, it isn't because people thought it was a heap of variables. You know, it isn't like a heap of laundry or something like that. I actually not quite sure why they use the word heap. Okay, but so stack kind of makes sense, but heap, BSS, text, they're kind of they were words picked back. They could literally go back to the 50s or 60s. So these are kind of oddly chosen words. Okay, but C is a name of a function, so that means it represents the address of this code that gets compiled to the machine code. So that would be text. Okay, now what about D? D is a local variable of a function. Those are stack variables. Okay, what about E? Okay, E is oh, now this one's a little bit different. This is a static local variable. Okay, see, it's got the word static in front of it. Okay, so static local variables are special. They are local variables, which means that this program can't see that variable. I'm sorry, this function can't see that variable. That variable only can be seen by main. Okay, if this function had a static variable, that static variable would only be visible to that function, not this function. Okay, it's local. But static means that it never goes away, that once the program is created, this variable exists, and then when the function is called and you return to it, the variable's still there. The variable doesn't go away when the function returns. Now, actually, it doesn't make sense to put a static variable in main. It's kind of dumb for me to. I should have put the static variable up here in C. I mean, this isn't wrong, but there's not much use for a static variable in main because you only call main one time. I should have put the static variable up here, because the idea is that every time you call C, if I put the static variable up here, every time you call C, the static variable would still be there with the value it had the last time you called it. Static variables preserve their value. They don't lose their value when you call them. When the function returns, the static variable doesn't lose its value. It remembers its value. The static variables are stored with the global variables. The static local variables are stored with the global variables. That way there's a place for them to sit all the time the program is running. If they sat in the stack, they would disappear, just like everything else in the stack disappears. So the static local variable is put in the data section along with the global variables. That way, when you call the function, its local variable is sitting there in the data segment. So the static variable never goes away. Okay. Then, okay, what about P? Okay. Well, P is a local variable. Now, this one's a little bit tricky.
Question.
P is this guy. He's a local variable. So the address of P is in the stack. Now, this would mean the value of P. So we're using, if you read this as C, this means the address of P. This means what's in P. When you write down a variable without any annotation in front of it, it means what's in the variable. But the variable is a pointer to int. So what's in it is the address of what it's pointing at. So what's in it is what's called its pointee, what it's pointing at. So it's pointing in the heap. So here's something in the heap. Something in the heap was allocated. Okay. So this thing, P, points into the heap. Okay. So this is the address of P itself, but P is sitting in the stack. This is what P points at. Okay. And you can actually, if you here's the C visualizer. Okay. There's our program. Okay. Get up to line 10. Let's see. what happened to P? Where's P? Huh. I didn't try visualizing this program before. Does the visualizer doing something wrong? Let's see.
I think you just have to scroll to the right.
Yeah, did it put it someplace? Oh boy, is that bizarre. I've never did this example in the visualizer. I didn't realize, boy, is that weird. Oh, that's a bug. There's a bug. It's not really a bug, but okay, so I can fix that by just making the array a lot smaller. Okay, so make the array a lot smaller. Okay, so there's P. Okay, now notice P doesn't have a value yet because I haven't gotten to that part of the code. Okay, right? See, now P is in main stack. See, this is the global variables. These variables would be over here in either the initialized data or the uninitialized data. Okay, so see, they're shown in their own little box. Actually, I think they made another mistake. I think they did that's really stupid. Notice that they put this under the word stack. That was really dumb of them. Okay, they should have put this box above or to the right over here somehow. But it's actually, I can see students getting very confused and thinking, well, okay, this side of the picture is the stack, so this is in the stack. But that's not the case at all. Okay, if you go back to this picture, they don't, this stuff here is just sitting in a memory location. It's usually near the text. It's usually right next door to the text. The stack is really someplace far away in memory. Okay, all right. And one thing that's a little bit interesting is this is correct. The command line arguments are at the base of the stack. That's actually where the command line arguments get put because they're local variables. So they're actually part of the stack, because if you think, what happens here is the command line arguments are a parameter to main. So they're actually a argument to main. So they're in the stack at the very beginning of the stack. So he shows it as command. He makes it look like they're not part of the stack, but in fact they're the base of the stack. The base of the stack is the command line arguments. So that picture is a little bit misleading, but it's right that the command line arguments are at the base of the stack. Okay. Now, this is confusing. The global variables are not part of the stack. Okay. So they should have been, this box here should have either been off to the right or maybe above this line that says stack and heap. Okay. Now, P is in the stack, but what P points at is in the heap. Okay, so the address of P, this would be an address in the stack. The contents of P is an address in the heap. So the address of P is in the stack, and the contents of P is an address pointing into the heap. Remember, a pointer means that there's a number here. The number is the address of this array in memory. Every memory location, we drew it here. Every memory location has a number. See, the numbers go from 0, 1, 2, 3, 4, up to 2 to the 34, for example. If you have if you have 4 gigabytes of memory, that would be up to 2 to the 34. So every memory location has an address. It's index in this array of bytes. That's what's in that variable. The number that is the address of that variable, of that thing in the heap. Okay. These are sometimes called dynamic variables. When you allocate something in the heap, people call it a dynamic variable because you create it and destroy it dynamically. I think that's actually a bad name for them. They should be called dynamic values. These guys aren't variables, they're values. But everyone refers to them as dynamic variables in the heap. But that's not helpful. Variables are these things over here with names. See, this thing doesn't have a name because it's not a variable, it's a value. The value of P is this address, and it points at another value that's in the heap. Okay, so that's what a pointer is. A pointer has a value, and its value is an address, and it's the address of another value that's in the heap. Okay, all right. So back over to here. Okay, so
a quick question.
Yeah.
Going back to E, would that actually be BSS and not data because it's uninitialized?
Yes. Yeah. I think. Yeah. Exactly. Which one? Oh, E, yes. Yeah, it's a static variable and it'd be a static variable in the BSS. Yeah, because it's an uninitialized static variable. You're right. Yeah, I probably forgot to mention that. It's, if you be really careful about this one, it's a static uninitialized static variable. So it would go in the what? It would go in the BSS. Okay. You can actually keep track of this. You can write this code to print out these addresses. So for example, this table here, you could just go right, you could add code to here and print out all these. Okay. I can't print all, well, actually, I can't print all of them from main, but I can print a little bit of it. So here, printf, the address of E equal, when you want to print out a pointer, you say %p for pointer. Okay? So that's, I'm going to print out a pointer. And what a pointer I'm going to print out is the address of E. Okay, that was one of these ones, address of E, because that one belongs to main. So I can print that out because that belongs to main. So there's the address of E. Okay, what else does main have? I could print out the address of P. Okay, now if I want, now look, now I'll change the value of P is that. See, that this is going to point into the BSS, this is going to point into the stack, this is going to point into the heap. Okay, the address of S. Okay, S is an array. Because it's an array, you can either say the address of S or you could actually just say S. Let me show you. I think you, let's try. Because the way arrays work, okay, should get the same answer. The address of an array is the value of what S represents. Okay, now that's all there is in main. On the other hand, I could take one of these and go up here. The address of D. Okay. Okay. And oh, let's see. Oh, the global variables. Sure, I can do the global variables. Could put, the global variables are here. So the address of A. Now A is an array, so it's the same thing. I could print it out. I should be able to print. I could either say the address of A or just say A, and the address of B. Okay. 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 Now just gather all those well, actually just hit last. Okay. So there's the output, and you can, see these. This is the stack area. If you look at this picture over here, they say like the stack is way up here. High addresses, see high addresses. Those would be addresses with a lot of Fs, 1111. So notice we're getting address FFFF. Those are very high numbers. That's a very large number. So that's high addresses. See, those are the things that are in the stack. P, S. Notice, see how these were exactly the same? Because if it's an array, the thing about an array is the address of the array is the same as the value of the array. That wasn't the case in P. See how in P, address of P and P mean very different things. So the address of P is that, and the value of P, see, this is a variable in the stack. There's something in the heap. So that gives you a sense of where the heap is. Okay. Now, A and B and D should all be, I'm sorry, A, B, and E should be close to each other because A, B, and E are all in the data segment, the two parts of the data segment. Okay. So A, B, and E should be similarly numbered. So there's A, B, and E, they're right next to each other. You can see that they're all very close to each other. You know, they're pretty close to each other. Um, let's see, A and E are very close to each other, and B is a little bit away. But A and E were the uninitialized one. So they're closer to each other because they're both in the BSS. And B is initialized, so it's a little bit farther away. So you can see how A and E are actually a little bit closer to each other, and B is a little bit farther away because it's in a different area. It's actually in the initialized variable where these two are uninitialized. That's why they're closer to each other. Okay, so you can actually watch this stuff happen. Yeah, this little thing here, print a pointer. Okay, you know, %p prints a pointer, and then you can pass it anything you want here, as long as you make sure these are addresses. Okay, and this is real instructive. Okay, there you know, you'll see lots of examples. If you Google these phrases like memory layout, like even this example here, this page here, they do examples just like what I'm doing here. They do examples of printing out uh, memory addresses and things. Okay, so they do it a different way, but you know, they do little code examples so you could see these things. Okay, all right. So if you take that code that was right in the problem, you can take the code, put it right in the visualizer, and you can actually, like, you know, essentially build that table too. Oh, actually, let me do one more thing. I mean, address of main, address of C. Okay, those can go in here too. Put them at the end. Actually, let's see if I do it carefully. What order did I have them? Oh yeah, just put it at the end. Okay, so I can ask for the address of main. Okay, and I just type main here. I could write an ampersand there, but it doesn't change it. It's like an array. Uh, a variable that's the name of a function is by definition the address of it. Okay, and I could also do the other function, which is C. The address of C is C. Go to the end. Okay. Notice that those numbers are close to each other. Okay. See that number there? That's the address of main in Windows for every single program. Every single program you run, the C compiler for Windows puts main at that address. It's fixed there. I'm not sure, it doesn't really need to be fixed there, but somebody at some point in Microsoft said, that's where we want to put main. And every program, unless you tell the compiler otherwise, there's a way to tell the compiler that you want to move main. But if you don't tell the compiler where to put main, for every program you run on Windows, the main will be at that address. That's the address of main in Windows. On Linux, it would have a different address, but I think on Linux it's the same. There's a fixed address that is where main goes. But this is where main goes on a Windows computer if you don't choose a different address. And then this is not far away because main's not very big. There's where the code for this program, the code for this function is at that memory address. Okay, and the code of main is at that memory address. Okay, so I can build this whole table. I can build this whole table. Now, this doesn't answer the question. This just gives me a bunch of numbers. Yeah, this doesn't tell me which one, if that's in, yeah. I can see from this that these guys are close to each other, but it doesn't tell me where they are. I can see that these are close to each other, the ones that, like this one, and this one. So I can tell that they're near each other in memory, but you have to know what the meaning of these words are to be able to say which one of these addresses are in which one of those. Okay. All right. So uh, that's a real good explanation of it. I mean, that's a very nice explanation of these ideas. So you can get that just by Googling, just Google these words, and this seems to be a pretty good site. I've been noticing lately that when I'm looking for explanations of things, I land on them and I find them pretty good. There's a lot of junky websites out there, and this one actually seems to be, to me, seems to be pretty consistently good at explaining things. I don't know who they are, but I kind of felt like that when I land on them and read them, they seem to be good at explaining things. Okay, so Oh, here's C static variables. Yeah, there's a, there they gave an explanation of static variables. Okay, and see here's but the static keyword in C++. And I was reading some of these a few days ago. They seem to be pretty good explanations. It's not organized as like a textbook or anything. It's just like little, everyone's a page by itself, but they do seem to be. I mean, I haven't found anything in them that was blatantly wrong. Where I do on a lot of other websites, I'll find things that are just, really poorly explained or blatantly wrong or poorly written. Yeah. But these seem good. So if you pay attention, if you see things for geeks, you might think that, that seems like a pretty good place for finding explanations of stuff. Okay. I don't know. Let's see. Yeah, and here's a bunch of stuff about C programs. I don't think it's organized. I don't think it's coming out of an organized textbook or anything like that. I think it just is a bunch of articles, but they do seem good. Okay. Now, any question about this one? So we talked a lot about this one. Any question? It's a lot. It's an important idea. Any question about it? The visualizer is great. The visualizer is really good. Yeah, the Java visual. This is the same people who did the Java visualizer. Yeah, it works in much the same way as the Java visualizer. It's really great. Use it. You can learn a lot by playing around with the visualizer. You can just, you just quickly type code, see it happen. You don't need a compiler on your computer. You don't need to be worrying about, saving files and things like that. Oh, and then if you got something that's good, you can always just copy and paste it into a file. So if you want to save this, you can copy and paste it. And here's a nice trick. The job visualizer looks like this. Suppose you wanted to send me something like this. Suppose you want to say, I did this on the Java visualizer. Here's something you can do. You can create a link to it. You see, you take this, and if you copy that, you can go like to another. If you can send that link to people in an email message, or for example, here I pasted in here. There's my program. The program's embedded in a URL. When you say here, you say create link to it. It creates a link to that code. It actually buries the code in here. See, this is your code. All this funny stuff here is that code encoded into a URL. So your code is encoded into a URL. That's why you have a lot of funny little symbols in here. So the code is encoded into a URL. You can send that URL as an email message. And then somebody could just, I mean, you can always send this text to somebody, but you can actually send them a link directly to the visualizer with your code in it. Okay. So you could copy and paste this code into an email message, but you could also just copy and paste this link. You can copy and paste that link into an, see, if I open a tab, I just paste that into the tab and hit enter, and there's that code. So you could send it to other people. You could, I do this to I make links in the course website. When I want to link to a visualization, the web page has the URL buried in it. Okay. So that was a clever little thing of them to do. They didn't have to do that. They could have just said, well, here's your code. You can save it in a file on your hard drive. But then, then it wouldn't be making use of the fact that this is a website. By doing this, it's making use of the fact that that's a web page. So now that makes this thing into a web page that somebody can point at. So that gives you the ability to point at it as a web page. Okay. And the similar thing is done with Pastebin and other places that store code for you. They have the same idea. They take the code in the web page and embed the code into the URL and then make the URL available. So Pastebins and GIFs, they all do the same kind of trick. Okay. So the visualizer is really good. Try to get in the habit of thinking of things in terms of how would I answer this using the visualizer? How could I use the visualizer to help me understand this? If you see code, it can probably be put in the visualizer. Okay, and that think that way. If you see code, you can think, well, what if I just put it in the visualizer and watch what it does? Okay. Okay, what about other problems from here? Or any more about this one? Any more about this one, or anything more about other problems from here?
S were both stack, right?
Pardon me? Say again?
S was both in the stack.
Oh, I forgot to do S.
You may have. I don't know.
Let's see. What did we put? Did I put S in the? Oh, here's S. Okay, so run it. I put S for string, not for stack. I was thinking. I was thinking here that S was for string. Okay, now go to last. Just run the whole thing. I don't have to step through it. Okay, S was, yeah. See those addresses, FFFF. Those are high addresses. That's a large number in hexadecimal. Notice it's got more digits. See, this is actually a number that begins 000. There's the same number of digits in both these numbers. They're addresses in memory. It's just that here you have leading zeros. Here you have leading Fs. That means it's at the high end, like that picture said. High end would be low end, this is address 0. This would be address FFFFFFF, all ones. This would be in binary. This is address 0000000. This is address 1111111. If you count from binary from 0 up to the end, you count from all zeros to all ones. Okay, so FF, you get used to this when you've been playing around with this stuff. You get used to FF being all ones. That's a high address. Okay, and so that's the stack. So here, this guy's in the stack. Okay, and it didn't matter if I said S or ampersand S. Same will be true for main. I can say main or ampersand main. I'll get the same answer. C will ignore the ampersand there. It will essentially ignore the ampersand there. And A is also an array. So in fact, I didn't need that ampersand there. So I can change this program. I didn't need an ampersand on A, and I can put them on B and C. When a variable represents when a variable holds an address, well, if the variable is a function or an array, then it doesn't matter. So I get the same thing here. Okay. So I could say either A or ampersand A, S or ampersand S, main or ampersand main. For arrays and functions, their name is by definition an address. So C will ignore the ampersand symbol. Okay. Or if you want, you can think of it as A will put in the ampersand symbol if you don't put it there. Yeah, you can think of it one way or the other. You can think of it as main is an address, so you don't need the ampersand symbol. Or you can think if you don't put the ampersand symbol, main, the C compiler puts it there for you to say, oh, you want the address of main. Okay, so it's just 6 of one, half does the other, whichever way you think of it. Same with C. C is an array. So usually you're taught to write it this way, that C is an array. So by definition, the value of C is the address of the array. But no, I'm sorry, that C is a function. I'm sorry, C is a function like main. So it was A was the array. A is an array. So by definition, the value of A is the address of the array. By definition, the value of that variable is the address of the array. So usually you're taught to just write A for the address, but you're also told that if you put an ampersand in front of it, it's still the address of A. It just becomes redundant. The ampersand is just redundant. Okay, right. So so this is data segment, stack. No, data segment. Yeah, because this one's a static one. Then stack, heap, stack, text. Okay. Okay. Other questions about this one or other review problems?
Can we do number 25?
Okay. 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 Runtime. That's how long the program. Well, okay. wall clock time, user time, kernel time. Okay. Wall clock time is how long the program from the start to the end. If you measure time using a clock on a wall or a stopwatch, it could be, I mean, they call it wall clock time. Maybe it would have been better to call it stopwatch time. If you use the stopwatch and you started the stopwatch when you started the program and you stop the stopwatch at the end of the program, how much time to evolve? But historic reasons, it was called wall clock time because I guess people spend a lot of time staring at the clock on the wall when they're at work. Okay, so wall clock time. How much time on the clock on the wall will elapse from the beginning of the program to the end of the program. Okay. Now, user time. User time is how much time this program spent running in user mode. Okay. Now, a good way to think about these times is, let me find that picture of process states. Okay, here's process states, right? Running, ready, blocked. Okay. User time and kernel time are time you spend in the running mode. But you could be running in either kernel mode or user mode. At any given time when your program is running, your program's either in user mode or kernel mode. If your program makes a system call, your program jumps into memory, but it's running, so then it'd be running in kernel mode. Then when the system call returns, you're back to user mode. Then when you make another system call, you jump into this OS, but it's your process that's running. You think of it as you jumped into kernel mode, then you jump back to user mode, then you jump into kernel mode, you jump into user mode. So your process could be running. So you're in the running state, but you could be alternating between user mode and kernel mode as you make system call. Now, if you make a system call that initiates an IO operation, you get blocked. Okay. Now, when you get blocked, you stop running and you go here. Okay. But then when you become unblocked, since you were blocked in the kernel, you'll pick up in the kernel, which is more kernel time, and then you'll return back into user time. Okay. So user time and kernel time are times you spend in the running state, and you're running either always in kernel mode or user mode. Okay. Then, okay. So now wall clock time would be actually the wall clock. Now, notice that if you're not in running state, you're in these two states. Okay. So your wall clock time is the sum of how long you were running, how long you were blocked, and how long you were ready waiting to get running again. So all your time is spent in one of these three states. So if you think about it, when your program is running, you're either running, blocked, or ready. So wall clock time is the sum of the time you're running with the time you're blocked with the time you're ready. Okay. The running time can be divided between kernel time and user time. Okay. All right. So you can think of them in terms of this picture here. Okay. Now, why is wall clock time almost never equal to user time plus kernel time? And the answer is this picture. Wall clock time is the sum of the time you spend here, here, and here. User time is the time you spend here. Unless you spend 0 time in these two, running time will be strictly less than wall clock time. Now, it's almost impossible for you never to be ready and never to be blocked. You can never be blocked by never making a system call, but you're still going to be ready sometime because your program, unless you're the only process on the CPU, which isn't very likely either, if you're the only process on the CPU, you might be able to run and never get descheduled. But if you ever get descheduled, then you'll spend a little bit of time over here when you're not running. Okay, so the question is, explain why wall clock time will almost never equal user time plus kernel time. User time plus kernel time is the time you spend over here. Wall clock time is the time you spend in all three states. Well, there's two other states to account for, so running time can't really equal wall clock time unless these two are both 0. You spend 0 time in blocked and 0 time in ready, but that's very, very unlikely. You can have 0 time blocked by just never making a system call. You write a program that does nothing but a loop that just does calculations, and it'll never block, but it's still going to be occasionally descheduled and put in the ready state so somebody else can run on the CPU for a while. So it'll almost always spend some time in the ready state. Okay. Now, suppose you have an IO bound process. Okay. So an IO bound process is a process that when it's running, it just immediately blocks itself. What we mean is by a good example of an IO bound process is a program that's copying data from one hard drive to another. Imagine a program that's just like if I just like, I open my computer and I go to some file, and I make a copy of it. If I make a copy of this file, so I do copy and paste. So I just be asking Windows to copy the file. That would be a purely IO bound program. It doesn't do anything to the data. It would just read a buffer of data, write a buffer of data, read a buffer of data, write a buffer of data, read a buffer of data, write a buffer of data. It doesn't do anything to the data. It just reads and writes it. Okay, so think of that as an example of a purely IO bound process. So what it means is as soon as it's running, it makes another IO call. So that would be, it's say, read a buffer. So then the buffer gets read. When the buffer's finished reading, you put in the ready, then it comes running. Then it says, okay, write the buffer you just read, because it's going to read from file A and write to file B. It's just copying. So think of IO bound meaning as soon as it's running, it immediately makes the next IO call. Okay, so it spends almost zero time running. So it spends vast majority of its time blocked and a little bit of its time ready, waiting for the next chance to issue another IO call. Okay, so now the question is, what kind of relationship would you expect to see between the three times? Wall clock time, between wall clock time, running time, and what was it? Well, wall clock time, user time, and kernel time. Okay. The user time and kernel time together are going to be close to zero, because the program just, as soon as it's running, it makes an IO, it does another IO operation. So it spends next to no time running. In fact, the majority of time it spends running will be in the system call. If you go back over this picture, it'll actually, what it'll do is it'll immediately make a system call, initiate the IO operation, and then become blocked. Then at some point, the IO operation will complete. When the IO operation completes, you return to kernel mode, finish kernel mode, and return from the system call, and then it makes another system call. So in fact, it spends zero time in user space, a little bit of time in kernel space, in kernel mode. So it's an IO bound process. The answer would be it spends next to zero time in user mode, a little bit of time in kernel mode, and a lot of time blocked. Okay, so the wall clock time would be almost all blocked time, a little bit of running time, and that running time would mostly be kernel mode. So the answer was, if the program would spend, the wall clock time would be about equal to the block time. The wall clock time would be pretty much equal to the amount of time it spent blocked. There'd be a little bit of time spent running, close to zero. And even of that time, most of it would be kernel mode rather than user mode, because the process would immediately jump into the kernel. The kernel would do some work to set up the IO operations, then block. Then the IO operation would complete. You'd spend a little bit of time in the kernel finishing up the IO operation, return to user space, which would then just immediately call an IO operation again and jump back into kernel space, do a little bit of work in kernel space, setting up the IO operation, issue the IO operation and block. When the IO operation completes, you go back to kernel space to finish up the IO operation, and then you return to user space, but then you make another call immediately. Okay, so the answer for this one, for an IO bound process, is that wall clock time is approximately the time spent blocked, okay, and user time plus kernel time is about zero, where and even most of that is still kernel time. Okay, then what about this one? A CPU bound process, that's a process that just sits here and computes up here, never makes a system call. It just sits here and computes. It has no reason to make any system call. So it's CPU bound. So let's imagine a process that's just computing and computing and computing and computing and never does any IO operation. Okay, so then the question is, what's the relationship between the wall clock time, user time, and kernel time? Okay, well, kernel time would be 0 or very, very close to 0. Okay, the user time would be very close to 0, and user time would essentially be wall clock time. The only difference between user time and wall clock time would be the little bit of time you spent in the ready state, when you gave up the CPU to let other people have their turn. So, there would be a little bit of time when the process is descheduled. So there'd be a little bit of wall clock time spent here, but the vast majority of the wall clock time would be spent running. So for a CPU bound process, kernel time would be 0. Running time would essentially be the same as user space time. So the running, and that would be close to wall. So wall clock time is approximately equal to running time, which is approximately equal to user time. Okay, so for a CPU bound process, wall clock time is approximately user time. Okay, kernel time is approximately 0. And the difference between wall clock time and user time is the little bit of time you spend in the ready state. Okay, so you can answer the question in terms of these states even. The question just said, explain the difference between these times. So you can explain how the times are related to each other, but you can actually also explain them in terms of the states. So for a CPU bound process, wall clock time is approximately user time. Okay, it's just the wall clock time is a little bit larger than user time, a little bit larger. Kernel time, almost 0. Kernel time's almost 0. You just don't spend any. The whole idea of what we mean by CPU bound is you don't call the IO op. You don't call a system. You don't make any system calls, so you don't go in here. Okay, and okay, so kernel time 0, user time is approximately wall clock time. Then the difference between wall clock time and user time is the ready time. Okay, the amount of time you spend in the ready state. Okay, so the point of the problem like this is to make you think of two things: this picture here and this picture. Oh, I'm sorry, this picture here and this picture here. Yeah, this picture here is the model of a computer for us. This is what a computer is doing. Your program, when it runs, is running on a physical hardware essentially like this. The CPU is always either in user mode or kernel mode. If it's in kernel mode, it's over here in it's in the kernel itself. If it's in user mode, it's in your code. So the CPU is bouncing between here, but it's also sometimes leaves your program and enters somebody else's program. When it leaves your program and enters somebody else's program, that's when you're in either the block state or the ready state. When it's running your program, you're in the running state. Okay, so think in terms of this picture, and put these two pictures together so that you have a really good mental model of how a computer works. And that work, it really does solve problems in the real world. When somebody says this program is slow and it shouldn't be, or how can we make this program faster, the answer is always going to be you have to analyze it from the point of view of this picture and this picture. You have to think, how often is the program blocked? What's blocking it? How does the program spend too much time in the ready state? What's going on over here? Am I making too many system calls? We kind of looked at some examples where if you make too many system calls, that can hurt you. You have to figure out what your program's really doing. Okay, so in the real world, when people start looking at the performance of programs, when their job is to say, okay, the program's correct, but we need to make it faster. Now you're in this world of looking at these pictures. These pictures don't help you make a program correct. And in almost any company, first you got to make the program correct. You got to get the bugs out. But it's real important in a lot of situations to make the program run faster. Always after you get the program correct, you might worry about making it run faster, and then this stuff comes into play. And the other place where this comes into play is when you need to make the program secure. That's becoming more and more important. People attack programs by exploiting problems with these pictures. If somebody makes a mistake in the layout of a program or makes some kind of mistake in the way that when this picture is implemented, that's where attacks happen. So almost everything to do with computer security is very low level, like this is, even lower level than this. Everything to do with computer security is really complicated stuff involving very low-level issues, because that's always where the attacks come from. They always come from exploiting some problem at this lower level. You almost never attack a computer at a high level. You almost never attack a computer by attacking somehow the code. You know, the attacks always come from these days. They always come from attacking something involving this low-level setup of the computer. Okay, so having this real good mental model, this is the basic model of what a computer is and what a process is, yeah, and relating this thing to this really helps a lot. I mean, and if you know, if you end up with a job where you are working with low-level stuff, then this is unavoidable. You'll be spending all your time thinking about this and this. Okay, all right. So okay, that was 25. Okay, okay. What about any other ones?
27.
Okay. Okay. The trick here is to there's a way of thinking of what this thing means. Okay. And let's see. Let me write something down. If you have an array A, okay, that symbol there, okay, we said a minute ago that when we looked at this example here, remember we said that that thing there can either be, you can either write the ampersand in front of that or not, okay? It means the same thing to write that as it means to write that. The variable A is by definition the address of the array. So these are synonyms for each other. The address of A is the value of A. Value of A in the case of not of a pointer but of an array name. Okay. So now you go over here, and what does this mean? This is the address of a memory location, but you want the ith element of the array. So what you want is the thing that has address A plus I. See, A would be the address of the first slot in the array. Okay, so for example, A0 is at address A plus 0. A1 is at address A plus 1. Okay, and A I okay. Okay, so you're stepping through the array. Now, the plus here is a little bit we'll say a minute ago what this plus means. Okay, but essentially I'm stepping through the array. Now, this thing is at that address. But if it's at that address, how do I get the data at that address? Well, I have to dereference that address. Okay? So AI means that. They're synonyms for each other. Okay? This means dereference the address A plus I. A is the address at the beginning of the array. Step that many steps through the array, which is the address farther in the array, and then give me what's in that address. So dereference that address. Okay. Now here's a cute little fact that this points out. You can actually do this in C. Addition is commutative, so this is you can actually write that because the addition is commutative. I plus A is A plus I. Okay. You can even check that. Go over here. A1, oops. A1 was put 7 in A1, and let's see if this compiler will accept this. Okay. Stupid compiler tricks. See? 2A was that memory location. Okay. Stupid compiler tricks. C is a weird language. C is just a flat out weird language. People don't realize how archaic it really is. Okay. Right. So, and then this is in the book on, if you go back to the books I've been giving you on references on C, and you read them line by line really carefully, you'll see that this is in there. They mention these facts. Okay. The meaning of this is dereference the address at the beginning of the array, that many steps into the array, dereference that. Okay. Now, the quirky thing is addition is commutative. So you can actually write this instead of that. And, we saw it here. It really works. Two square bracket A. Okay. Because what we've really done, here, I'll do another one. Dereference A plus 3 or plus 0. I'll just do it 1. Okay. Equal 22. Okay. So now I'm using that other notation. This is the same thing as this would be A1. Okay. A plus 1 dereference it. Boy, the visualizer is slow today. Okay. Step through. Okay. I set A1, A2, and then I set A1 again. Okay. See, it's got 22 in it. So notice that I got 3 ways of accessing the array. I think I've mentioned in class before. There's the Obfuscated C programming contest. Who can write C code that's the most unreadable? It's actually an international contest to see who can write the most unreadable C code. And people do some utterly amazing things. That's a C program. That's actually not one of the worst ones. There's a C program. Can you figure out what it does? Probably not. The whole point of the contest is, can you make a program that's unreadable? That's a C program. That's one of the tricks, is to make ASCII art out of your C program. That's an international winner because that's pretty amazing. You can do crazy things in C. You can make your code as unreadable as you want. Okay. You can start with what you're supposed to write. Then you can start playing around with what you shouldn't be writing, and you can make your program as unreadable as possible. So you have this famous international obfuscated C programming contest. And usually the prize goes to someone who can create a nice ASCII art out of their program. Okay, so that's a good one. Yeah. Oh, there's another cute one. Good luck trying to ever figure out what that program actually does. And you can download it and compile it. I doubt if you could put this into the C visualizer. It probably won't work if you put it into the C tutor. I never tried the C. Oh, the library, yeah, the visualizer doesn't have the right library. Yeah, see, that library is not part of the visualizer. So that stops us from being able to run the program in the visualizer. Okay. But you might be able to find some of these that will actually load in the visualizer if they don't load any libraries. Okay. All right. So C can be notoriously hard to read. Okay. So that's one of the things about C. All right. Now go back to that problem. The problem is literally understanding what arrays do. So it's about understanding this. That's what the problem is about. That the meaning of the ith element of array is you take the base of the array, you move that many steps into it, that gives you an address in the array, and you dereference that address. Okay, so now go back to that problem and figure out which one of those do the right thing. Okay, all right, so here's, okay, a plus I isn't enough because a plus I just is that. So that's not the equivalent of this. Okay. Now, what is, this says a plus I times size of a, 0. The thing is here is, go back over here, and I could make a, okay, here's several declarations of a. Okay, think of it that way. Or if I want, maybe I should make that an A, a B, and a C. So I have 3 arrays. Okay. So then down here, okay, this is, well, here's what's interesting. This plus 1 does not mean the same as this plus 1, does not mean the same as this plus 1. Here, plus 1 means 1 int. Here, plus 1 means 1 double. Here, plus 1 means 1 char. But an int is 4 bytes. So that means it's really adding 4 to A, because this is 1 int, so that's 4 bytes. So it actually increases A by 4. And this is 8 bytes. And this one is 1 byte. So this plus 1 really means, I'm sorry, plus I means I bytes. Well, it means I ints, which is I times 4 bytes. Plus I means I doubles. So you have to skip over I doubles. So that's I times 8 bytes. And this means I chars, which means I have to skip over I times 1 byte. Okay, this is called pointer arithmetic. I here is how many doubles to skip over, but each double is int. Each int is 4 bytes. Here's how many doubles to skip over. In general, here's what this means. AI equals the dereference of a plus I where plus I means I times size of whatever's in the array. Okay, it's a little bit tricky. See, it's I times the size of whatever's in the array. See, this is I times, the size of int is 4, the size of doubles 8, the size of char is 1. Okay, so this means I times the size of whatever's in the array. That's where this guy's coming from. Okay, so you can say, you can put that as size of whatever's at the beginning of the array. So I wrote as A0 there. Means I times the size of whatever's the first thing in the array, whether it's an int, a double, or a char. Okay, so now what that does is it does the same, that is the same thing as this. A plus I is by definition pointer arithmetic, so that's exactly what that thing does here. But that still only gives you an address. See, it's missing the dereference. So this one's not right. Okay. This one takes the address of I and address of A and adds I to it. Okay, that's the same thing as this. Well, actually, it's the same thing as this, because remember, A is the same thing as address of A. So it's this, so this one and this one are the same thing, and they're still not that. Okay, there's the one that is that. Okay, so that one is it. Okay, now this one, well, A0 is the contents of the first thing in the array. So you can't put this, you can't put that in place of that, because this means the address of A, the first slot. This is the contents of the first slot. So that's not the same thing. This is wrong. Ah, but this is right. Because A is the address of the beginning of the array. A0 is the first thing in the array. The address of A0 is A. So this one is correct because A0 is the first thing in the array. The address of it is back to being the address of the array. So it's the same thing as that. Okay, so that one's correct. Okay. This one, that one is actually correct because you take the ith slot in the array, you take the address of the ith slot and dereference it, and you're pointing at the ith slot. Okay, so that one would be correct because you're taking the address of the ith thing in the array and then notice that these guys just undo each other. You're dereferencing the address of. So star ampersand just undo each other. They're inverses of each other. Take the address of something, then dereference that address. So if you put a star ampersand in front of anything, it doesn't change it. Okay, so that they just cancel each other out. Okay, this just gives you the address of a location and not what's in it. Okay, then these here, we'll quit. We run out of time. These are playing games with this thing here. They're trying to do the pointer arithmetic directly. Okay, they're doing the pointer arithmetic of saying that you take the address of A, you add to it a number of steps of how many bytes there are. So that's these pointer, these casts here. When you cast something to a pointer to char, you're actually getting byte addresses. Okay, so that makes this pointer arithmetic here byte arithmetic. Instead of being pointer arithmetic, it becomes byte arithmetic. So if I remember right, this one is right and this one is wrong. But I can't remember now. We run out of time to analyze these. Okay, one of these I think is correct. But it's playing a game with this trick here that this thing means that. You know, this means that, where what does this mean? This means add I times the size of the first element in the array. Plus I means, well, plus that. Okay. Okay. So we run out of time, so we should quit here. Okay. All right. So these come out of this trick, this little trick that, you know, the basic trick is that what we did in the program over here, that you can, that's what array, that means that. And it actually can mean that too. If you want to play stupid tricks, you can, since addition is commutative, you can flip those around and get that there. But it's important to know that that means that. Okay. So the homework assignment is based on using the fact that that is just a synonym for this, and then asking you to sort out these different almost right ones. Most of these are almost right, but only a couple of them actually are the same thing as that. Okay. Okay. So, oh, actually, the exam is ready. If you look, the exam's probably you can download it at this point because it's past 1:45. Actually, has anybody tried? Anybody tried?
Yeah, it's available.
Okay, great. Okay, good. That's a good test. So it should be downloadable at this point, and it's due at 11 o'clock this evening. I have classes this afternoon, but if you send me emails asking questions like clarifying, I'll try to answer them as soon as I can. So I'll try to answer questions during the day. If you have if you need something, if you have a question about whether you're misunderstanding a problem, yeah. If you ask me, is this the right answer? I'm not going to answer questions like that on an exam. But if you ask, am I, if you ask like, is this the right way to interpret this problem? Or am I, if you're thinking you might be misinterpreting the problem, I'll tell you whether you're on the right track or not. Okay. So, I have classes, so I may not be able to answer emails right away. Okay. So, okay. So we'll go ahead and quit there. I'll put what we did today up on the website. Okay. I'll try to put up, like this, not that one, and not that one. I'll put this code up on the website as a link to the visualizer. So I'll put this up on the website as a link to the visualizer, just like we did it here. Okay. Any last question? Anybody have a last second question before we quit? Okay. So I'll go ahead and stop sharing and have a good exam. Have a good weekend, and we'll meet again on Monday. Okay. Bye-bye.